So today I'm going to be talking about designing concrete pavements, best practices for doing so. So when I talk about designing concrete pavements, I always like to start off with this picture and this question. Design for what? You can see here we've got a great picture of, something that you start doing a crosswalk, it starts going pretty well, but when you don't think through the entire design, you can run into this situation where you have a roadblock right in the middle of your crosswalk. So it's thinking about all those different things, all those different design aspects that really make a good design a good design. So that's what we're going to try to talk about today and hit the highlights on designing concrete pavements. So we start off, let's think about all the different design considerations that we might have. We've got geometrics, we've got curb and gutter, we've got shoulders. You can see different pictures of those, and these are actually from all across the world. We've got El Salvador here, Mexico here, actually the U.S., San Francisco there with the top left here. All of those are things that we think about in design, but may not be that much different from, say, an asphalt design that we're a little more used to doing in some situations. So the concrete side may be, fairly similar to that. Similarly, if we're thinking about traffic, climate, drainage, other things like that, a lot of the things that we do with concrete would be very similar to what we have to do with asphalt. So the consistency from one to the next makes it fairly easy to do a concrete pavement in just about all types of situations because we've seen concrete pavements used in all types of situations. So that's what we're trying to do here. So we can really do just about anything with concrete that we do with asphalt. The things that are a little different in design for concrete pavements are what we're going to spend a little more time talking about. Those design considerations that are specific to concrete that we're going to focus on today are thickness design, jointing, and materials and mixture design. So within thickness design, the first thing that we have to kind of think about is which design program or guide are we going to use? How is that going to impact what we can focus on and how we can optimize the design? We also have to think about the structural response and the support underneath our concrete pavement because that's going to change how we can optimize our concrete as well. Additionally, when we get into jointing concrete pavements, jointing is something that's very different with concrete, how we actually control the stresses in our concrete pavement, what our joint spacing needs to be, how we lay out those joints, especially in complex, say, intersections or roundabouts, or even just having a left-hand turn lane. How do we handle those how do we handle the jointing in those situations? And then also Dowel and Tiebar design. How do we make sure we have good long-term load transfer in our pavement? That's another thing featured in jointing as well. Materials and mixture design, we won't spend too much time because Mike and Gordon talked about that in the last session quite a bit. But it is an important thing that's a little different when we talk about designing concrete pavements that should be considered as well. So starting off with the first thing is thickness design. So thickness design is really what I think about when I think concrete pavement design. And so I always think about these three main tools for designing concrete pavements. Now, two of them are probably ones that anybody who's designed a pavement are familiar with. That's AASHTO 93 and AASHTO Ware's Pavement ME, which is the current pavement design tool that a lot of state DOTs are really using now, the AASHTO Ware Pavement ME. It's a great tool for design. The other tool, pavementdesigner.org, is a free tool for designing concrete and cement-based pavements. That's one we're actually going to talk about in tomorrow morning's session. So we won't spend too much time on that, but it's a good, important tool to know as well. And so I bring up those three because it's important to understand the differences between them. And the biggest difference is that AASHTO 93 design guide, as you can guess from the name, is from 1993. So it's already about 27 years old, but it's actually older than that because it's really based on the AASHTO road test in the late 1950s, early 1960s. So this design guide is actually based on one road test from Central Illinois, and it's all of the entire design is based on the observations of that road test. And so what it's really designing for is performance serviceability index. So that's really how it defines failure, which is kind of difficult when we think of how concrete pavements actually fail, which is a lot of times cracking and faulting and sometimes in roughness as well. And so when we move past that AASHTO 93 design guide, you can consider it a 40-year divide between that old empirical design methodology and our current mechanistic empirical design softwares in Pavement Designer and Pavement ME. But with those new design softwares, we can actually look at how pavements distresses develop over time and cracking and faulting. And with Pavement ME, we can do IRI too. So when we look at concrete pavement structural response, we have that cracking, we have that faulting, we have roughness as well. We're really trying to figure out how to optimize our design such that we mitigate these distresses developing in our pavement. So how do we actually impact the cracking performance of our pavement? What can we do to optimize our pavement design with this? The first thing that impacts cracking, the most important thing, is actually the thickness. Makes sense. The thicker our pavement is, the lower our stresses will be within that pavement, and that'll reduce the risk of cracking occurring in our pavements. We're reducing those stresses. Additionally, the next most important thing is our mix design, really our strength and our stiffness. What are our material properties that are going to impact the pavement's performance? And that's really one of the biggest things about cracking performance. Next few are still important, but not quite as important as those first two. It's our joint spacing of our pavement. As you can imagine, if we take our 15-foot joint spacing and move it down to 14 or 13 feet, just like Jamie talked about with the new road test, how they're testing 17-foot joint spacings, 13-foot joint spacings, and had a couple 15 in there as well, even the 6-foot by 6-foot joint spacings. The reason we do that is because when we change the slab size, we're actually changing dimensions of our pavement, which will change the stresses that develop in our pavement. Additionally, with some of those, you can actually change how many axles our pavement's being exposed to at one time, which is going to further change the stresses. So it's an important thing to think about. Additionally, we have climate, which isn't going to change no matter, if we have a project, we have to deal with the climate situation. We also have lane width, which again changes the dimensions of our pavement and can also get our pavement or get our truck traffic off of the edge of our pavement, reducing our stresses. We also have a shoulder design. You can imagine if we have a concrete shoulder, those two can actually help share the load a little bit and help reduce the edge stresses on our pavement. And then finally, support stiffness. So you'll notice the last thing on there, the thing that's not quite as important, is that support stiffness. What is the actual underlying layers that are helping impact our pavement performance? Now, faulting design is quite a bit different than our cracking design. What can we do to mitigate faulting? Because they are two very different mechanisms. When we think about faulting, what really impacts the design is our dowel design. So what dowels are we using within our pavement? The size of our dowels, are they 1.5-inch dowels, 1.25-inch dowels? It's going to change how our pavement performs. Additionally, the spacing of those dowel bars, a lot of times we're at 12 inches on center, maybe 6 inches or a foot off of the edge of our pavement. That's a pretty good design. It's what's pretty standard across the country. Then we have our joint spacing. If we change our joint spacing and reduce our joints down a little bit, that can again impact our faulting performance. We have lane width, which again is getting back to that idea of stresses and how our pavement's responding to that. And then we have support system. So our support system, what the erodibility of that support system really is, can impact the design as well. And that gets into the idea of pumping. Pumping is really what leads to faulting. You can see in that top picture there where we've got moisture as well as fine grained material getting pumped out of our joints. That's what's going to lead to faulting. So if we can reduce that by reducing the erodibility of our underlying layers, we're going to make a better pavement as well. And finally, thickness. And this one is actually inverse from what you would expect and inverse from what we saw with cracking. Whereas if we held everything else constant, all of our pavement thickness design, everything else is constant, we may see that a thinner section might actually perform better than a thicker section just in faulting performance. And that's because our dowels may become more effective. So these are all things that we can analyze and look at with that Pavement ME software. And that's why Pavement ME is such a robust tool for designing and analyzing concrete pavements. So now, I want to touch on that support system because you'll notice that support system in both the cracking and the faulting were a lot lower on the totem pole than some of the other design elements. And that may be counterintuitive to people that are more, have a better background in asphalt pavement design, and that's because concrete and asphalt transfer the stresses and the load down into the substructure differently. Concrete distributes it over a wider area, and so you see much lower stresses or much lower pressures on the subgrade and subbase below it, whereas asphalt, a flexible system, uses that underlying system together, and you see higher pressures going in there, and you see that load actually penetrate deeper into the structure. So that's why I show this figure you see in the bottom right here, where you can see if you greatly improve or greatly change the stiffness of the underlying structure of a concrete pavement, it's not going to change the required thickness a whole lot. And that's why we don't really recommend recommending spending a whole lot of time stiffening up the substructure. What we really need more is uniformity of the substructure to get a better design for our concrete pavements. Okay, so next up we got jointing design. Now, jointing design is something we spend a lot of time talking about. How do we make sure our joints perform well? So the reason we have those joints in our concrete is to control where the cracking actually occurs within our pavement. Because every time we see one of those joints, we've got a crack underneath there. extending from the bottom of the saw cut. That's by design. That's where we're controlling where those cracks are actually developing. Additionally, when we have these joints, it's to divide the concrete into constructible length. See in the bottom left picture, if we had, say 3 lanes wide or 4 lanes wide, we wouldn't really want to pave it, or we may not want to pave that in one pass, so we would have to construct it in multiple passes. So that's what joints are in there to do as well. And so accommodating slab movements is another reason why we joint concrete pavements. And so you can get back to that with what we talked about in the cracking and faulting design. If we change the dimensions of our slabs of concrete, it changes the stresses within our pavement. And so when we accommodate slab movements, that's going to accommodate the expansion and contraction with thermal and moisture cycles. Additionally, if we control the joint spacing and control the slab movement by decreasing our joint spacing, we're also going to control curling and warping effects. So that's another good impact that we can see with designing our joint systems appropriately. Additionally, if we didn't know where our joints were, we wouldn't be able to know where to put our load transfer devices, our dowel bars, to make sure we get long-term load transfer. And finally, if we're sealing our joints, we'd also have to know where that sealant goes, and that's another reason why we have our joints within our concrete pavement. So in terms of designing our jointing system, the first thing that's on there is joint spacing. Talked about a little bit with designing and our thickness design programs. One of the big things, limiting the stresses within our pavement, but also the types of joints. This is something as designers we can't really control a whole lot. That's more on the contractor to figure out where these different types of joints are going to come in. But it's important as designers to know that they're going to have to be in there somewhere within our pavement, especially when we get into intersections and roundabouts, how those joints are going to be laid out. We have to understand that all of these different types of joints may be needed. So we've got contraction joints, which we can see up here in the top right. Different types of contraction joints, whether they're longitudinal or transverse. We can have dowel bars in them, Tiebars in the longitudinal ones, or if we have thin pavement that doesn't have a lot of truck traffic, we may just have aggregate interlock in there. When we have construction joints, these would be those flat face joints, which would be in between paving lanes or happen as a header at the end of a day of paving. A lot of times you'll see these either be doweled or tied. You'll likely see some kind of steel in there at the construction joint as well. And then the final main type of joint is our isolation joints. These are going to isolate two sections of pavement from one another, or say isolate our pavement from an in-pavement structure. So you can see different schematics of those. We've got a lot more information on those as well if you want more detail. The last couple types of joints are more transition joints. You see these from concrete to asphalt, or say a terminal joint when you're coming up to a bridge, something like that. Don't see them a whole lot, but they obviously have their place as well. Then we have load transfer and edge support, which we'll talk about in just a second, and joint layout, which we'll go through a little bit more in a second as well. So load transfer and maintaining joint continuity. This is your idea of how do we get the slab, or how do we get load from one slab to the next and keep it smooth. So we want a smooth surface as we go across our joints. We don't want our driving public to feel that transition from one joint to the next. So we have a few different ways where we transfer load. And so the first one is through aggregate interlocking. See a great shot of what that looks like here with the picture where we've got that saw cut, and underneath that saw cut our pavement cracks just like we want it to. You can see how those aggregates kind of cross that crack to help share the load from one slab to the next. This works pretty well for lower volume roads or places where we don't have a whole lot of trucks. But as our slabs expand and contract, you can imagine how that may wear away a little bit. Additionally, with significant truck traffic over time, you could see aggregate interlock wear away over time as well. That's why we have mechanical load transfer devices, or dowel bars in our system. Those are meant to be long-term load transfer devices, really meant for transferring that load from one slab to the next, especially with those when we have heavy loaded trucks. I always like to mention that tie bars, while we use them a lot in our longitudinal joints, they're not really there for load transfer. They're more there to keep that joint tight, make sure we don't get our lanes separating a little bit from one lane to the next. Keep everything nice and tight, keep those longitudinal joints tight rather than transferring load. We don't really need load transfer from one section to the other in the longitudinal direction. It's not quite as significant as our transverse direction as we drive forward. And finally, the last thing for load transfer is sub-base support. And this is kind of misleading because sub-base support isn't really going to improve load transfer. What it's really going to happen, or what it's really going to do is decrease the differential deflection from one slab to the next. So the differential deflection between the two slabs may be decreased if we have a higher support system or a stiffer support system underneath our pavement. But again, that's not really what we should not really how we should go about designing our pavement. We should really be focused first on looking at the dowel bars in the system as well. Alrighty. So looking at our dowel bar design, what we're really looking for is looking for faulting resistance and load transfer. You can see here what those dowels are exactly in there to do, where we have our 0% load transfer. What we're looking for is actually 100% load transfer, or very nearly that, somewhere in the 90s. High load transfer efficiency is what we're looking for out of our dowel bars. And, excuse me. And when we design our dowels correctly, we get good load transfer for long term. We've got a bunch of different types of dowels that are, a lot of them are meant to be long-term load transfer devices, even in harsh climates. So that's what they're really there for. So when we look at designing for our load transfer, we're really thinking about the size and spacing of those load transfer devices. Additionally, we can get into shape and material, especially if we have a really thin pavement, but we still want load transfer devices in there. You may think even about plate dowels or something like that. Most of the time, we're talking about our conventional round dowel bars. So if you're looking for a little more information besides just what you would see in a spec book, there's a dowel design tool called DowelCAD, the free tool. You can find it at the link there, acpa.org/DowelCAD. So when we think about Tiebar design, again, what we're looking for is to keep that joint tight, not really for load transfer, just keeping those two sections of pavement together and not letting them drift apart. So here again, we're looking for size and spacing, embedment depth of those tie bars to make sure that those two slabs aren't drifting away. There is another tool that you can find on Dowel bar or Tiebar design at apps.acpa.org. Another has a few tools, including a Tiebar designer for just that situation. So joint design. A lot of times when we think about joints, the first thing that comes to my mind, at least, is these complex joint geometries where we start to get into, say, an intersection or a roundabout or even a diverging diamond interchange. Really anywhere where we don't just have, our rectangular area where we can just, do squares or rectangles all the way down the pavement. Here we have to actually think about how do we lay out our joints to make sure that we get good geometries such that we reduce the risk of cracking. And so for that, ACPA has a few step-by-step guides for how to actually design these joints. So the first one is the 10-step method for jointing intersections. You can see here the result of going through those 10 steps. You can see you get a pretty good joint layout where most of our joints most of our joints are square as much as possible, rectangular. We move those odd-shaped panels out into the edges of our pavement, trying to get them out of the main directional travel. Additionally, when we have roundabouts, we have 6-step methods for roundabouts. You can see a couple examples of those, the isolated circle or the pave-through method. Additionally, you can find the 10-step method, the 6-step method, and the diverging diamond interchange method here at this link here at the bottom on our WikiPave website. If you look at wikipave.org and look at joint layout, you'll find all of these online that walk you through each of the steps for designing these layouts. So the last one is the diverging diamond interchange. This one's a little wonky, but it really takes a good layout to get these things to perform correctly. So you can see two different methods for that, the pave-through method and the quadrant method. Again, these are online at wikipave.org, and if you look at joint layout on that site. So the last thing that I want to touch on is materials and mixture design. Really, Mike and Gordon did a great job talking about this in the last session, talking about performance engineered mixtures. There's a lot of goals with performance engineered mixtures, but including durability, but it's also about constructability as well, how our pavements respond to vibration, and making sure that when we have a mixture design, it's pavable in addition to delivering those performance criteria that we want as designers. So we have to have both sides of that. So you can see here, we want to optimize based on the tarantula curve or shieldstone chart, making sure when we optimize our aggregate gradation, what we can also do is reduce our paste content. It's going to help increase our durability and reduce our shrinkage. And additionally, it's going to improve our pavement's performance as well. If we can take some paste content out there, it's likely going to increase how quickly our pavement's going to develop strength as well. So we really want to kind of avoid using accelerated mixtures except for where we absolutely have to, primarily because a lot of times when we do accelerated mixtures, we additionally will need to avoid just adding a bunch of cement in there because that's where we do tend to have some durability concerns as well. Inclusion of fibers, Jamie mentioned that they're incorporating that into the FDOT concrete road test, which is great. Another great thing to see with materials in terms of concrete pavement design. So in terms of mixture design, what we're concerned with as designers on the structural side is looking at what is our strength, what is our flexural compressive strength, additionally, what's our stiffness, modulus elasticity. All of these things get back into that pavement design that we just talked about, making sure that our design properties are in that mixture design, making sure we're getting what we need. And then finally, properties as well, property altering additions such as fibers, chemical admixtures, mineral admixtures can change the pavement design as well. So when we're looking at our goals, again, it comes down to making sure that our design goals and our construction goals line up together. When we have uniformity and consistency within our mixture, we're going to be able to pave it a little better, making sure that it responds to vibration, making sure that it can go through our paver and come out well consolidated and not segregated. It's really what we're looking for on the construction side, because that's the only way we're going to still make our performance goals as well. So with that, just a little quick summary on the thickness or on the things we're concerned with concrete design. First thing is our thickness design. Understand that it's the same tools a lot of times as our asphalt design, but different approaches. Changing our thickness or changing the support underneath our pavement may not change the actual concrete pavement performance. So you really need to look at those other properties that we mentioned as we went through there. Additionally, joint design, spacing matters. It's very significant within our pavement's performance, but we also need to be concerned with load transfer as well as joint layout. Those three step-by-step methods, I encourage you to look at them if you're doing a joint layout for an intersection or a roundabout, or even if you're just dealing with a left-hand turn lane and not quite sure how to make sure those slabs work well for that. These step-by-step methods can be applied for a lot of different scenarios, not just what they were originally intended. And then finally, mixture design, you need to make sure it meets design and construction requirements. So with that, thanks for your attention. We're going to do questions at the end, but appreciate your attention.